What specific problem does the novel method PAD address within the framework of dataset distillation, and how does it improve upon previous methods?
The novel method prioritize alignment in dataset distillation PAD addresses the specific problem of misaligned information during the dataset distillation process, particularly in the two steps of information extraction and information embedding. PAD improves upon previous methods by implementing a data selection strategy that filters out samples based on their difficulty, ensuring that only data aligned with the compression ratio is used for distillation. Additionally, it employs a parameter selection module that focuses on using only the parameters from deeper layers of the agent model, which capture higher-level representations, thus avoiding the redundancy introduced by shallow layers. Experimental results demonstrate that these strategies significantly enhance the quality of the synthetic dataset, leading to state-of-the-art performance across various datasets and compression ratios. Overall, PAD effectively mitigates the issues of misalignment that compromise the quality of distilled data in existing matching-based methods.
How does the proposed method PAD work? Please illustrate the methodology step by step, particularly focusing on the information extraction and information embedding phases.
The proposed method, prioritize alignment in dataset distillation PAD, operates through two main phases, information extraction and information embedding. 1. Information extraction. In this phase, PAD employs a data selection method to assess the difficulty of each sample in the target dataset. It ensures that only samples whose difficulty aligns with the desired compression ratio, IPC, are used for training the agent model. This is crucial because previous studies indicate that easy samples are only necessary at high compression ratios, and including misaligned samples can degrade the quality of the distilled dataset. 2. Information embedding. During this phase, PAD modifies the traditional approach by utilizing only the parameters from the deeper layers of the agent model for distillation. This is based on the observation that shallow layers provide low-quality, redundant signals, while deeper layers capture higher-level representations essential for generating high-quality synthetic samples. By filtering out shallow layer parameters, PAD effectively reduces the introduction of misaligned information, thereby enhancing the overall performance of the dataset distillation process. Through these steps, PAD successfully aligns the information extracted and embedded, leading to improved synthetic dataset quality.
Can you provide a simple yet illustrative example of how PAD operates during the distillation process, highlighting the role of the data scheduler and parameter selection module?
The prioritize alignment in dataset distillation PAD operates through a two-step process that includes a data scheduler and a parameter selection module. For instance, during the information extraction step, the data scheduler first assesses the difficulty of samples in the target dataset using the error L2 norm EL2N score. It then ensures that only samples whose difficulty aligns with the desired compression ratio, IPC, are used for training the agent model, gradually incorporating harder samples as training progresses. In the information embedding step, the parameter selection module masks out shallow layer parameters of the agent model, which typically provide low-quality signals, ensuring that only deeper layer parameters are used for distillation. This combination of filtering misaligned data and focusing on high-quality parameter signals significantly enhances the quality of the synthetic dataset produced by PAD.
What theoretical or practical benefits does PAD offer compared to existing dataset distillation methods, particularly in terms of performance metrics and computational efficiency?
The prioritize alignment in dataset distillation PAD method offers significant theoretical and practical benefits over existing dataset distillation methods, particularly in performance metrics and computational efficiency. Theoretically, PAD addresses the misalignment issues in both the information extraction and information embedding steps by employing data selection methods to filter samples based on difficulty and by utilizing only deep layer parameters for distillation, which enhances the quality of the synthetic dataset. Practically, experiments demonstrate that PAD achieves state-of-the-art performance across various datasets, outperforming previous matching-based methods, especially when the compression ratio exceeds 1%, indicating improved performance metrics. Additionally, the filtering mechanisms in PAD not only enhance the quality of the distilled data, but also contribute to computational efficiency by reducing the amount of redundant low-level information processed during distillation, thus streamlining the training process. Overall, PAD's alignment strategy effectively improves both the performance and efficiency of dataset distillation, making it a robust advancement in the field.
How was PAD validated or tested in the experiments? Specifically, describe the datasets used, the experimental design, and the evaluation metrics that demonstrated the method's effectiveness.
PAD was validated through comprehensive experiments conducted on widely recognized datasets, specifically CIFAR-10, CIFAR-100, and Tiny ImageNet. The experimental design involved comparing PAD against several prominent dataset distillation methods, categorized into matching-based approaches like DC, CAFE, and DATM, and kernel-based approaches such as KIP and FREPO. The evaluation metrics included performance comparisons based on the effectiveness of the distilled datasets across different compression ratios, IPC settings, where PAD consistently outperformed previous methods, particularly at higher IPCs. Additionally, ablation studies were performed to assess the isolated effectiveness of the filtering modules, FIX and FIEM, within PAD, further demonstrating its efficacy in removing misaligned information and improving distillation performance. The results indicated that PAD achieved state-of-the-art performance, validating its effectiveness in dataset distillation.
What key results were achieved with the PAD method in comparison to traditional dataset distillation approaches, and how do these findings contribute to the advancement of the field?
The prioritized alignment in dataset distillation PAD method achieved state-of-the-art SOTA performance across multiple datasets, including CIFAR-10, CIFAR-100, and Tiny ImageNet, outperforming traditional matching-based methods and demonstrating superior results, particularly at higher compression ratios, IPC. The experiments indicated that filtering out misaligned information during both the information extraction and information embedding steps significantly improved the quality of the synthetic datasets, as evidenced by the enhanced performance metrics reported. Specifically, PAD's approach of selectively using deep layer parameters for distillation and employing a data scheduler to align sample difficulty with the compression ratio led to more effective learning and representation of high-level features. These findings contribute to the advancement of the field by providing a robust framework for dataset distillation that addresses the critical issue of information misalignment, thereby enhancing the efficiency and effectiveness of synthetic dataset generation. Overall, PAD not only improves performance, but also offers insights into the importance of parameter selection and data difficulty alignment in the distillation process.